Okay, sports fans. So, I have 8 lectures to record today. 8. So we're gonna see how many I can actually get through, and edit and whatever's okay. Again, I hope this new audio quality is better. Got a new mic, so All right. So today we are going to talk about operations on polynomials. Okay, but before we do that, we should probably define what polynomials are, some properties about them, all that good stuff. Okay, so what is a polynomial? So let's start with the definition. Let's call it P, okay? P, actually. Okay, ready? Start again. An expression P is a polynomial if and only if. Definitions are always if and only if. So, if, it is of the form, ready? A sub 0, actually, ready? A sub j, x to the j, plus a sub j minus 1. So like, we'll get to what that means in a bit. To the times x to the j minus 1 plus da 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 a sub 0 x to the 0. Okay? And here are your caveats. A sub j is not 0. Okay? J is a positive integer. That's it. Those are the conditions. Okay? Now, what do I mean by a sub j? And da 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 da. We'll get there in a second. Okay? So let's give an example first. Let's say my polynomial is going to be 3x to the 5th plus 7x squared plus 2x to the 1st plus 8, right? Okay. My j value is equal to 5 because it is the highest exponent we have, okay? And all that means is that this is the jth coefficient, okay? So like, yeah, that's it, okay? Your leading coefficient can't be 0 unless it's the 0 polynomial. We'll get there in a second. J must be a positive integer, so no negatives. Yeah. So basically, this binds us to a couple things. One, all exponents are non-negative integers. Okay. 2, coefficients. And a coefficient is just the number being multiplied in front of the variable. Okay, so your coefficient here is like 3 or 7 or 2, right? Our numbers. And 3, a sub 0, x to the 0 is also sometimes called c, which means constant. So like plus 2, plus 4, plus 8, whatever. And it can be 0. All right? Big picture, that's all right? And of course you can have an equation is a polynomial, right? Like you can say like, oh, p of x is equal to this guy. Or a function, it can be a polynomial function, so on and so forth, okay? So let's talk about, in detail, the different parts of a function, or of a polynomial, okay? So if we go back to a sub j x to the j, again, this has to be the biggest term, and I'll tell you what I mean by biggest, plus a sub j minus 1. You will not see me write this as a sub j minus 1. This is just a generalized form, okay? So like this is the coefficient that deals with the 7th, with x to the 7th. This is the coefficient that deals with x to the 6th, so on and so forth, okay? X to the j minus 1. And of course, this can always equal 0, right? You can always have like 3x to the 7th plus 0 x to the 6th, which would just be written as 3x to the 7th. Okay, that's perfectly fine. And then you have a sub 1 x to the 1, which can be written just as a sub 1x, right? So it could be like 3x, 10x, pi x, whatever, right? Plus a sub 0 x to the 0, which, like we said, can be the constant, right? So let's say this is your polynomial, just as generic as you can get, right? If you notice, this is going to be the biggest exponent you have, right? So whatever the biggest exponent you have is going to be j, and j is going to be your degree. It's also called the degree of the polynomial. Even polynomials behave symmetrically on both sides. They either both go up or both go down. Odd polynomials are asymmetric. One side goes up, one side goes down. We'll talk a little bit more in detail about that later, okay? Okay, second, if j is your degree, and the degree of the polynomial, right, then a sub j is your leading coefficient, okay? Whether it's positive or negative will also affect the behavior of the graph, okay? And we'll go back to that in a second. And finally, you have a sub 0, x sub 0, right? Oops. Which you can also call c, which I will also call c as well, okay? A sub 0, x to the 0 is equal to c, which is your constant, okay? So each of these individual pieces, right, so like this, 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 and this, these are all called terms, okay? These are all called terms. Like this is the jth term, for example, right? All right, let me rephrase that. This is called the first term because we read left to right. So this is the first term, this is the second term, okay? Okay, so let's talk about special types of polynomials, okay? So the word polynomial means many names, okay? So this is many, these are names, okay? And it's called a polynomial because many, and then each of these pieces are the nomials, okay? So what kind of polynomials can you have? Well, you can have a monomial, which has one term. So for example, you can have x squared. You can have 1/3 x cubed. You can have pi x to the 8th. You can have 0. This is called the 0 polynomial. I won't be testing you guys on the naming convention, but I do expect you guys to be able to use it confidently, because I'll be using it throughout these lectures, okay? you have your binomial, bi meaning 2. So you have like x to the third plus 3, 1/10 x to the 8th plus 5, so on and so forth, right? You have your trinomials, and I'm going to have you guys take a guess as to what trinomials mean, okay? Tell me on Gradescope. Tell me on Gradescope what you think a trinomial is, and some examples. That's it. That's definitions of polynomials, okay? Next, we're going to cover what you can do with a polynomial, okay? So the first thing we can do is adding, okay? You can add them. Some key things to, I suppose, recognize. 1, we only add, like combine, like terms, okay? So for example, let's not do an example. Like terms include same variable with the same degree. Okay, let's do an example. If I say, oh, 3x squared plus 2x, can I simplify this? No, I cannot. Although this is technically adding, right? We're not putting these two together any further. There's nothing more you can do because this is x squared, there's a 2 here, and this is x to the first. There's a secret 1 there, right? I will not be writing the secret 1, but if it helps you, please do so, okay? Now, what if I said 3x squared plus 2x plus 8x squared plus 5, right? Okay, let's look at the two binomials and see what we can do, all right? Can we combine any more like terms? Well, if we look at it, we see, oh, there's a 3x squared here and an 8x squared here, okay? If I have 3 apples and 8 apples, we can add them. We cannot add apples and oranges. Fair enough? So if we add these two together, you should get 11x squared, okay? My personal preference is to go by degree. So I start with the highest degree and I go down the line. So if x squared, the 2 is the highest degree, the next one I want to look for is x to the first, okay? So we'll see how many x to the first terms I have. In this case, I only have 1. So nothing else to do, we could just write that down. And then what if, let's see, this is x to the first, let's look at x to the 0, which is just the same as the constant term. How many constant terms do we have? We only have 1. Plus 5. And that's it. You're done. As a quick aside, if you want to know why you're allowed to combine like terms, ready? If you confuse easily, ignore this, okay? You're saying 3x squared plus 8x squared, right? What you can actually do is factor out the x squared, right? You can undistribute, right? So if you factor out the x squared, you'll end up with 3 plus 8 times x squared, right? So we distribute this out, go this way, right? And then, well, we have MDAS, 3 plus 8 is 11. That's all. Another way to look at it, if the left and right bother you, is you can say, oh, 3x squared plus 8x squared, you can factor the x squared on the left side. This is called left and right factorable. In fact, not all systems can do that. You will never have to worry about it, but left and right factor. If you factor the x squared, end up with 3 plus 8, right? 3 plus 8 is 11. X squared times 11. This is commutative, so you can swap the order, and this gives you 11x squared. We love algebra. Okay? So, if you do confuse easily, you can tune back in now. All right? We can add them. That's it. This is how you add. But Amanda, what if I have a subtraction sign? I'm so glad you asked, because you can also subtract them. Subtraction is just inverse addition. I don't believe in subtraction, personally. I'll show you an example, though. Let's say, for example, you have 4x cubed plus 8x squared minus 1, right? This minus 1 is fine. It is okay. It's okay, all right? Okay, and let's say I want to subtract 2x to the third minus 6x plus 5. Hear me out. Why subtract when you can inverse add? Really, subtracting and inverse adding, okay. Okay, what does it mean to subtract? Fundamentally, right, if you're saying this one minus this one, you're really saying this one plus the negative version of these guys, right? So actually the best course of action is to FOIL, okay? It's to distribute that negative sign out. Please don't mess it up. It'll be very bad if you do. If you don't feel confident with distribution, I strongly recommend you do a lot of practice, okay? So if we distribute the negative sign out, you end up with minus 2x cubed plus 6x minus 5. Of course, if you want to write it as like plus negative 2x cubed plus 6x plus negative 5, you're more than welcome to. I don't see why you would, but you're welcome to, all right? And then from here, we combine like terms as usual. Are there any x cubed terms? Yes, there are. 4x cubed minus 2x cubed is 2x cubed. Probably should have picked better numbers, but it's okay. And then are there any x squared terms? There's only one, okay. Plus 8x squared. Are there any x to the first terms? Yes, there are. Plus 6x. Are there any x to the 0 terms or constant terms? Yes, there are. We have minus 1, minus 5. Negative 1 minus 5, or negative 1 plus negative 5 is negative 6. And you're done. Ain't that beautiful? Okay, what else can you do? I'm so glad you asked. You can multiply them. You know what? You can multiply them. Ooh, exciting. How? How do we multiply them? Okay, ready? Do you remember Punnett squares? I hope you do, right? Like if you're looking at like, oh, the first set of genetics has the options of A, B, and the second set of genetics has an option of A, right? You can go like this, and then like this, and like this, right? And so this slot, this combination will be AA, this combination will be AB, this combination will be AA, and this combination will be AB, right? Same exact idea. It's a combination problem. It's very exciting. And of course, right, if you remember with Punnett squares, let's say you had A, B, and A, B, right? You'll get AA, AB, let's try that again. You'll get AA, BA, AB, BB, right? If you do probability on this, right, you'll notice that everyone accepts that these two are the same, right? You'll have 1 AA, 2 ABs, because AB and BA genetically are the same, and 1 BB, right? Multiplying polynomials is the exact same thing. Hear me out. X squared plus 6x times 3x plus 1, right? Let's do some distribution. We'll distribute this first, okay? So I'm actually going to color code all of the pieces for you. So I'm going to call this pink, I'm going to call this orange, I'm going to call this blue, and I'm going to call this green, okay? So if we were to distribute, going like this, right, we have a pink-blue term. So we have x squared times 3x, all right? And we also have a pink-green term, right? So we're going to add plus x squared times 1, just like that. Now we'll work on the second term, the orange term. What are the combinations? You'll have plus 6x times 3x, and you'll have plus the term 6x times 1. Of course, you don't have to start with pink. You can start with orange. You can start with blue and go backwards, as long as you keep them in pairs. So like this goes here, and then this goes here, right? You're okay. And if you notice, right, everyone who is in a group already does not get distributed with each other. There is no need, right? But everyone in different groups gets a combination. It goes back to our Punnett square analogy, all right? And so from here, I'm going to strongly insist that you simplify, okay? So once you get here, it's kind of smooth sailing. You just start, you have all of the pieces being multiplied together. Let's actually properly multiply it out, okay? So what's x squared times 3x? That should be 3x squared. Plus x squared times 1 is simply x squared. 6x times 3x is going to be 18x squared. And 6x times 1 is 6x. For the first, if you were so inclined. All right? Okay, we're not done yet. We still have to add them together. We have to combine like terms, okay? So now let's go in with a lighter purple and see what we have in common. Ooh, just kidding. That's not a 3x squared. That's a 3x cubed. Because this and that, okay? All right, now let's go in and combine like terms. Are there any other x cubes? There are not. And I actually recommend you either color code the like terms or like do a different symbol. So sometimes I'll do boxes and like squiggles or whatever, okay? Okay, are there any other, let's see, are there any x squared terms? Yes, there are. There are 2 of them. X squared plus 18x squared is going to be 19x squared. Are there any x to the first terms? Yes, there are. There is only one, and that will be 6x, and that's all our terms, and we can call it quits here, okay? That's how you multiply. But Amanda, what happens if our polynomial has different variables? That's okay too. Let's do an example. Let's say I have 2xy, 2 is a bad number, 3xy plus 7 times, actually 7y times 2x plus y cubed. Okay? Same exact process. I'm going to color code. Again, you don't have to, as long as you stay organized. I don't care what you do. So I'm going to call this 1. I'm going to call this 2. I'm going to call this 3. Let's pick a nicer green. I'm going to call this 3. I'm going to call this 4. Okay? So my first term I will have as going this way. That'll be 3xy times 2x. My next bit will be this going this way, and that'll be plus 3xy times y cubed, yeah? Yep. And then my next term is going to be plus 7y times 2x. And my last term is going to be 7y times y cubed. As a little tidbit, if you follow this process, right, and you're not combining as you go, okay, if you follow this process, you should end up with number of terms total is equal to number of terms in first group times number of, and by groups I mean like a set of polynomials, or a set in parentheses, okay? Terms in second, times number of terms in the last group, okay? If you don't combine as you go, you should end up with that many. So in this case, I should end up with 2 times 2, which is 4. And I do, in fact, have 1, 2, 3, 4, okay? I'm going to tell you the philosophy behind why this works first, and then I'll show you the shorthand after, okay? If you understand the philosophy of why this works, you will never make a real mistake. You will only make silly mistakes, okay? I prefer silly mistakes over real mistakes, all right? But mistakes in general are okay. Fundamentally, right, 3xy times 2x. 3xy is just saying 3 times x times y, right? 3 times x times y, and then this piece, of course, is times 2 times x, right? We live in what the mathematicians call a field, which means you have the commutative property. You can squish things around, right? So you can actually swap the order. This is the same as saying 3 times 2, move the 2 over, right? Times x times y. Okay, 3 times 2 is 6, we know that. X times x is x squared. Nothing to do with y, so we just leave like that. You end up with 6x squared y, okay? Like I told some of your classmates, once you understand this and you do it enough, it will become muscle memory. And you don't actually have to manually think about it. It's like driving a car or riding a bike or your morning routine, okay? And so, let me give you an example of muscle memory. I look at this. Okay, the coefficient here is a 1, so I could just say 3. There's no x on this side, so it's x. There's a y here and a y here. It's y to the first and y cubed, so it's y to the fourth. But intrinsically, this is what I'm doing in the background, okay? And we do it again. 7 times 2 is 14. X times y is just xy. Let's do it again. 7y times y cubed is going to be 7y to the fourth. Okay? I'm able to do it fast because I have this as muscle memory. Okay? I don't even have to think about it. All right? And that's more or less it for multiplying polynomials. It's quite straightforward. No notes. Let's talk. How many operations have we done? We've done addition, subtraction, multiplication, and we're missing division. We're missing division. So let's talk about that. Okay? Now, there's harder division. It's called polynomial long division, which I will not be teaching you. We do not have time. Okay? And then there's monomial division, and that's easy. That's very easy. Okay? So let's do an example of that. Suppose I have 3x squared plus 6x plus, 3x squared plus 6x all over 3x, right? The first thing you will not ever do is go whoop 2. Don't do that. The second thing you will not do is whoop x to the first. Don't do that. We are civilized humans, okay, friends? We are civilized mathematicians. Let's do it the right way. I want you guys to look at the greatest common factor of the top and the bottom. If you can't get the greatest, get the second greatest, okay? I know vibes-wise, right? I know vibes-wise that this is divisible by 3. And so is this, and so is this. So let's factor out a 3, okay? And this gives us x squared plus 2x all over 3 times x. Okay. And like we talked about the other day, 3 divided by 3 is equal to 1. Don't ever tell me cancels out to 0, okay? We're civilized. Okay. Well, if you do that, you end up with x squared plus 2x all over x. Let's try to take another factor out. I see x to the first on the bottom, And both of these terms, okay, my friends, have an x as well. So let's factor that x out. X plus 2 all over x. X divided by x. This is a dangerous game to play. When you're working for solutions, be very, very careful. When you're working for solutions, when you divide things out, you end up losing solutions, okay? Or you end up losing asymptotes. We'll get to that later, okay? For now, this is fine. Okay, x divided by x is equal to 1, and that leaves you with x plus 2. Okay? Reasonable. The book recommends you divide each term by the bottom, and I think that's super sketchy. I would not recommend, okay? Like, they're like, oh, just divide this and then divide that. Most of you guys will forget and will only do one. I strongly recommend you do this, okay? Now, you're probably asking, but Amanda, this takes forever. It takes forever because we need practice, okay? I'll show you how I do it once you get enough practice in, okay? 12x cubed plus 8x squared plus 4x all over 2x, right? I know that all of these are divisible by 2, this coefficient, and all of these are divisible by x, okay? They have at least one x as a factor and a 2 as a factor, okay? So immediately I'm going to write this as 2x, 6x squared plus 4x plus 2 all over 2x. And then the process is the same. Oh, 2x over 2x is 1. And that leaves us with 6x squared plus 4x plus 2. Okay? Polynomial division. It's very nice. You'll never actually divide polynomials in this very specific way to solve a problem. This is a skill to build up to rational functions, which we'll get to in about 3 lectures, okay? Okay, before we move on to the next bit, let's work this problem out together, and I do want you to submit this to Gradescope as well. Okay, this is gonna be an Amanda question, all right? So, work this out, and then I'll work it out after. So hit pause, come back to me in a second. Okay, if you're back here, you already hit pause, so let's get into it. What I would do is I would not color code because I'm tired of color coding. If you guys need it, please feel free to do it yourself, okay? I would say, oh, this distributes here, so that's 3/3 x squared, right? I'm going to distribute this going this way, which is going to give me 15xy, right? And then I'm going to do the bottom, go like this, and that's going to give me 4/3 xy, and I'm going to go, you might be tempted to write this as yx. That's okay, that's fine. And you're going to do the last bit, which is going to give you 20y squared. If you got stuck here, and I didn't mess up, if I messed up, please comment or let me know or whatever. If you got stuck here, please slow down, go back to it, and just get very confident with distribution, okay? And then from here, I'm going to simplify because some of the bits are a little funky looking. 3/3 is just 1, so x squared plus 15xy plus, and I'm going to rewrite this as xy as well instead of yx. They are the same, but I'll show you why it's nice to have it written in the other order in a second. Plus 20y squared. Okay? Now, as I promised, this is the same as this, yeah? The reason why we want that is so it looks a little bit more like this guy. Because when we go to combine like terms, there's no x squared terms, there's no y squared terms, so nothing to do there. But there is a pair of xy's, okay? So if we were to combine this, this gives you x squared plus this is a fraction, this is not. That's okay. Let's turn it into a fraction with a common denominator of 3. All right? So this becomes 45 xy plus 4/3 xy plus 20y squared, right? And then we can just combine them down. One, I'll make note of it so you see. And this should give you, well, again, nothing happens to the x squared. 45 over 3 plus 4 over 3 is 49 over 3 xy plus 20y squared. And you're done. Okay, so for your work problems, for grade school purposes, we're going to be on page 98, which is the problem recognition exercises. I think they're more encompassing, they're a little bit better. I want you guys to do numbers 1 to 3, 5 to 12 odds, okay? You only have to submit the odds. If you want to do the evens, be my guest. 17 to 19, 21 and 32, okay? Okay, that's it.